This lecture is basically second part of probability theory. Okay. So in this lecture, we will cover NCERT section 14.2, 14.2.1 to 14.2.3. Okay. So these sections we'll cover in this lecture. So this is disclaimer. So first, we will discuss axiomatic approach to probability. Okay. So we will discuss about axiomatic approach to probability first, and then we will discuss probability of an event. Okay. And then we will discuss probabilities of equally likely outcomes. And lastly, we will discuss probability of the event A or B. Okay, that is also called A union B. So probability of A union B, and this rule is called addition rule. So we will discuss at the end of this lecture. So make sure you have with your notebooks and pens ready. So let's start. First topic, axiomatic approach to probability. Okay. So in earlier sections, we have considered random experiments. Okay. So we have discussed about random experiments, sample space, and events associated with these experiments. Okay. So I hope you all have studied about random experiments, sample space, and events. Okay. And related the concept of this topic are clear to all of you. And in our day life, we use many words about the chances of occurrence of events. Okay. So we use this odd chances of occurrence of events. Okay. That is actually called probability of events. Okay. So probability theory attempts to quantify these chances of occurrence or non-occurrence of events. Okay. So probability theory basically describe explain actually chances of occurrence or non-occurrence of events. Okay. And in our earlier classes, we have studied some methods of assigning probability to an event, okay, associated with an experiment, like rolling a die, flipping a coin. Okay. So that etc. We discuss how to assign probability to an event, okay, associated with an experiment. Now, axiomatic approach. So what do you mean axiomatic approach? So axiomatic approach is another way of describing probability of an event. Okay. So this is another way of describing probability of an event. So in this approach, some axioms or rules are depicted to assign probability. Okay, so we will first discuss some axioms or rules that will help us to depict to assign probability. So let S be the sample space. Okay, so what is sample space? So we have studied about sample space. So sample space is nothing but the set of all outcomes of an random experiment. Okay. So we let here S be the sample space of a random experiment. Okay. And what do you mean? What do you mean random experiment? So we will know an experiment where which outcome will come, we don't know in advance. Okay. But we know all the possible outcomes of that experiment. Okay. So this type of experiment is called random experiment. Okay. So we let here is be the sample space of a random experiment. So now the probability P is a real valued function. So probability of an event. Okay. So before discuss about that, the what is P here? So the probability P is a real valued function. Okay. So you all know the definition of real valued function. Okay. So the probability P is basically a real valued function whose domain is the power set of S and range is the interval close interval 0 comma 1. Okay. So P is nothing but a function that we call here real valued function, and domain of the function P is the power set of sample space S. Okay, and the range is the interval 0 comma 1, and then satisfying the following axioms. Okay, so note down first axiom. So for any event E, probability of E is greater than equal to 0. Okay, so probability of an event is always greater than equal to 0. That means probability of an event cannot be negative. Okay, it always positive, and you can say here for any event E, P of E is greater than equal to 0. Clear? And second axiom. So if we take probability of sample space, so that must be equal to 1. Okay, so probability of S must be equal to 1. And the third axiom, if E and F are mutually exclusive events. Okay, so you will know all about mutually exclusive events. Okay, so you all have studied in previous class what is mutually exclusive event. Okay, so if if we have two events, suppose E and F. Okay, so if intersection of the event E and F is empty, then E and F are called mutually exclusive events. Okay, so if E and F are mutually exclusive events, then P of E union F, this is equal to P of E plus P of F. Okay, so students, note this axiomatic approach. Okay, so here note this point. P is a real valued function. Okay, so pay attention, pay close attention at this point. P is a real valued function, and what is the domain of P? The domain of the function P is the power set of sample space S. Okay, and what is the range of P? The range of P is P is basically interval 0 comma 1. Okay, and then note down three axioms. First axiom, for any event E, P of E is greater than equal to 0. Okay. Second axiom, probability of sample space S equal to 1. And the third axiom, if E and F are mutually exclusive events, then P of E union F, this is equal to P of E plus P of F. Clear? So it follows from 3. Okay. Third axiom. So it follows from third axiom that P of phi equal to 0. That means probability of empty set is 0. Okay. So how can we prove P of phi equal to 0? So to prove this, we can take the event F equal to phi. Okay. And here note that E and phi are disjoint events. Okay. How can you show E and phi are disjoint events? So you can check intersection. Okay. So E intersection phi must be phi. Okay. So E and phi, these two events are disjoint events. And therefore from axiom 3. So in axiom 3 we have seen if E and F are mutually exclusive events, then P of E union F equal to P of E plus P of F. Okay. So from axiom 3 we get P of E union phi. This is equal to P of E plus P of phi. Okay. And here you can see P of E union F. Okay. So P E union P union phi. So P union phi is basically E. Okay. So E union phi is nothing but event E. So probability of E union phi is equal to basically probability of E. Okay. So P of E. So we get this equation P of E equal to P of E plus P of phi. Okay. And now from here we will obtain P of phi equal to 0. Okay. So P of phi equal to 0. So we have proven P of phi equal to 0 by using axiom 3. Okay. So note this point, probability of phi. Okay. Probability of empty set is always 0. Clear? So this point is very important point. So note this point, all students. So I hope there is no doubt. Okay. So we will now move to next slide. So in this slide, first we let here A's be a sample space containing outcomes omega 1, omega 2 up to omega n. Okay. So we first here let A's be a sample space and A's containing outcomes omega 1, omega 2 up to omega n. Okay. So Ace is nothing but the set omega 1, comma omega 2, comma omega 3, comma up to omega n. Okay. And it follows from the axiomatic definition of probability that, so we have learned about axiomatic definition of probability. Okay. So it follows from the axiomatic definition of probability that probability of omega I. Okay. So probability of all the outcomes should be lies between 0 to 1. Okay. So probability of omega I always lies between 0 and 1. So we can say here 0 less than equal to p of omega I less than equal to 1. For each omega I belongs in sample space S. Clear? And then according to second axiom, probability of omega 1 plus probability of omega 2 plus dot 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 plus probability of omega 1 n, this is equal to 1. Okay. So in axiomatic definition of probability we have seen second axiom, that is a probability of S equal to 1. Okay. And here S is nothing but the set omega 1, omega 2 up to omega n. So probability of omega 1 plus probability of omega 2 plus dot 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 plus p of omega n, this is equal to 1. Okay. And it follows from third axiom of the axiomatic definition of probability, for any event A, P of A, this is equal to summation P of omega I, where omega I belongs in A. Okay, clear? And it may be noted that singleton set omega I is called elementary event or sample simple event. Okay, so what is simple event? So an event which has only one sample point from sample space S. Okay, then it is called simple event. Okay, or elementary event. So singleton set omega I has only one sample point. Okay, so singleton set omega I is called elementary event. Clear? And for notational convenience, we write here P of omega I. Instead, P of set omega I. Okay. So we write for notational convenience always like this. P of omega I. Clear? So I hope axiomatic approach, okay, of probability, okay, axiomatic definition of probability is clear to all of you. Okay. So now we will take an example related axiomatic approach to probability. Okay. So for example, in a coin tossing experiment. So we are taking here as a random experiment a coin tossing. So if you toss a coin, then which are possible outcomes? So if you toss a coin, then you will get either head or tail. Okay. So we are we have taken here random experiment a coin tossing. Okay. And we can assign the number 1 by 2 to each of the outcomes h and t. Why? Because there are two outcomes in coin tossing. Okay. So equal chance to occur when we toss a coin. Okay. It may be head or it may be tail. Okay. So 50-50 chance. So here we can assign the number 1 by 2 to each of the outcomes h and t. So what is the probability of head? Okay, so what is the probability of getting head? So we assign here 1 by 2 to each of the outcomes h and t. So p of h equal to 1 by 2 and p of t equal to also 1 by 2. Okay, are you getting point? And clearly this assignment satisfies both the conditions. Okay, so you can check here both the conditions. Okay, so each number is neither less than 0 nor greater than 1. Okay, so always here you can say 1 by 2 is greater than equal to 0, greater than 0 and less than 1. Okay, so this assignment satisfy the condition. Okay, that is p of p of e. Okay, of an probability of an even p of e is always greater than equal to 0 and less than equal to 1. Okay, so it satisfies it. So you can check here also second condition p of h plus p of t. So if we add probability of getting head and probability of getting tail, then you will get 1 by 2 plus 1 by 2 equal to 1. Okay, and therefore in this case we can say that probability of h is 1 by 2 and probability of t is 1 by 2. Okay, so in a coin tossing experiment we assign the number 1 by 2 each of the outcomes h and t, and then we assign here p of h equal to 1 by 2 and p of t equal to 1 by 2. Okay, and then we verified the conditions. Okay, so p of h, p of t is greater than equal to 0 and less than equal to 1. Okay, and we added p of h and p of t, then we obtain 1. Okay, so it satisfied all the conditions. So in this case we can say that probability of h is 1 by 2 and probability of t is 1 by 2 also. Okay, clear? So if we take p of h equal to 1 by 4 and p of t equal to 3 by 4. Okay, so now we can assign the number 1 by 4 to getting outcome as head. Okay, and we can assign here the number 3 by 4 to getting to get as a outcome tail. Okay, so we assign here p of h equal to 1 by 4 and p of t equal to 3 by 4. So now we will check what is the probability of H and probability of T. Okay, so let's check here. So does this assignment satisfy the conditions of axiomatic approach? So students, try to check, does this assignment P of H equal to 1 by 4 and P of T equal to 3 by 4 satisfy the conditions of axiomatic approach or not? Okay, so check that. So here you can see, yes, in this case, probability of H equal to 1 by 4 and probability of T equal to 3 by 4. Why? Here you can see the conditions of P of H and P of T always greater than equal to 0 and less than equal to 1. Okay, so satisfied first condition. And if we add P of H and P of T, then you will obtain 1. Okay, so it satisfies also second condition. So in this case, probability of H equal to 1 by 4 and probability of T equal to 3 by 4. Okay, and now we find that both the assignments P of H equal to 1 by 2 and P of T equal to 1 by 2, and second assignment, uh, P of H equal to 1 by 4 and P of T equal to 3 by 4 are valid for probability of H and T. Okay, so both the assignments are valid for probability of H and T. Clear, students? So in fact, we can assign the numbers P and 1 minus P to both the outcomes such that 0 less than equal to P less than equal to 1. Okay, so we can assign this number P and 1 by P to both the outcomes, and here P lies between 0 to 1. Okay, and here you can see P of H plus P of T, this is equal to P plus 1 minus P, and this is equal to 1. Okay, so this assignment too satisfies both the condition of the axiomatic approach of probability. Okay, so what can we say? So hence we can say that there are many ways, okay, rather infinite ways to assign probabilities to outcomes of an experiment. Okay, so there is not only finite ways, there is infinite ways assign we can assign the numbers to outcomes of an experiment. Okay, so now for clearing this concept, we will now consider some examples. Okay, so by help by helping of examples, we will try to understand this concept. Okay, students, so now let's take an example. So students, look at example number 4. So insert it example number 4. So first read the example very carefully, okay, and see what we have given in table. Clear? So let a sample space be S equal to omega 1, omega 2 up to omega 6. Okay. So S containing the outcomes omega 1, omega 2, omega 3 up to omega 6. Okay. So which of the following assignments of probabilities to each outcome are valid? Okay. So we have to check here, uh, amongst the 5 assignments, which of the following assignments of probabilities to each outcome are valid? Okay, so we will take this. So students, first of all, think about this example. How would you approach this example? So you have 10 seconds to think about this example. So let's try to find which of the following assignments of probabilities to each outcome are valid, okay, and which of the following assignment are not valid. So let's check. So you have 10 seconds. Okay, I hope you have checked which of the assignments or probabilities to each outcome are valid. Okay, so let's see how to check. Okay, so first check assignment A. So in assignment A, we have given here 1 by 6. Okay, this number assigned to omega 1, 1 by 6. Okay, and omega 1, omega 2, omega 3, omega 4, omega 5, and omega 6. Six outcomes are assigned to 1 by 6, 1 by 6, 1 by 6, 1 by 6. Okay, this number. So each of the number p of omega I is positive here. Okay, so here you can easily see here each of the number is positive and each of the number are less than 1. Okay, each of the number is less than 1 also. Okay, so now condition 2, check condition 2. So now take sum of the probability. Okay, that means add p of omega 1, p of omega 2, p of omega 3, plus p of omega 4, like this, up to p of omega 6. Okay, so take sum of probabilities, that is equal to 1 by 6 plus 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 1 by 6. Okay, 6 times 1 by 6. So you can easily calculate it and you will get this is equal to basically 1. Okay, so this must be equal to 1. So here assignment A. Okay, so assignment A here satisfied condition 1 and also satisfied condition 2. Okay, so condition 1 and 2 both are satisfied by assignment A. So therefore the assignment, okay, this assignment is valid. Clear? This assignment, first assignment, is valid, student. Clear? So now we will check second assignment. Assignment B. See here. First check condition 1. So in assignment B, here you can see P of omega 1 is 1 and P of omega 2 equal to P of omega 3 equal to dot 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 equal to P of omega 6. Okay, all are 0. Okay, so each of the number p of omega I is either 0 or 1. Okay, and here you can see each of the number here p of omega I is greater than equal to 0 and less than equal to 1. Okay, so it satisfied condition 1. And then take condition 2. Okay, now take sum of the probabilities. Okay, so sum of the probabilities equal to basically 1 plus 0 plus 0 plus dot 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 up to plus 0. Okay, and this is nothing but equal to 1 by 1. Okay, so this is nothing but equal to 1. So here sum of the probability is equal to 1 and each of the number is either 0 or 1. Okay, so it satisfied condition 1 and condition 2. So therefore the assignment B is also valid. Okay, so assignment A is valid and assignment B is also valid. Okay, so now we will check assignment C. Okay, so let's check assignment C. So first of all, observe the assigning numbers. Okay, uh, here you can see in assignment C, we p of omega is 1 by 8, p of omega 2 is 2 by 3, p of omega 3 is 1 by 3, and p of omega 4 is 1 by 3. Okay, and p of omega 5 equal to 1 by minus 1 by 3. Okay, so and p of omega 6 is minus 1 by 3. Okay, so here you can see minus 1 by 4, 1 by minus 1 by 3 we have. So you can see condition 1, two of the probabilities p of omega 5 and p of omega 6 are negative. Okay, but it's not possible to get negative numbers. Okay, in case of probability p of some outcome. Okay, so but here we have p of omega 5 and p of omega 6 are negative. So what we can say? So we can say here condition 1 not satisfied. Okay. So the assignment is not valid. So we can say here the assignment C is not valid. Clear? Now check assignment D. Okay. So here you can see P of omega 1 is 1 by 12, P of omega 2 is also 1 by 12, okay, and P of omega 3, P of omega 4, and P of omega 5 is equal to 1 by 6, and P of omega 6 equal to 3 by 2. Okay, so let's check first condition. So here you can see P of omega 6 is 3 by 2, okay, and 3 by 2 is equal to basically 1.5, 1.5, okay, and 1.5, this number is greater than 1. But we have studied axiomatic definition of probability. Condition 1, probability of probability of some outcome must be always lies between 0 to 1. Okay, it cannot uh, it cannot greater than 1. So here but we have here P of omega 6 is 3 by 2, and this is greater than 1. So what can we say here? So therefore the assignment is not valid. Okay, so assignment D is not also valid. So assignment D is also invalid. Okay. So now we will check assignment E. So in assignment E, here you can see P of omega 1 is 0.1, P of omega 2 is 0.2, P of omega 3 is 0.3, okay, and P of omega 4 is 0.4, P of omega 5 is 0.5, and P of omega 6 is 0.6. Okay. So here you can see if we take sum of the probabilities. So what we will get sum of the probabilities. So if we add these numbers, then you will obtain 2.1. Okay, 2.1. This number you will get. So sum of probabilities is 2.1, and this is not equal to 1. Okay, so it should equal to 1, but it is equal to 2.1. So what can we say? So we can say here, therefore, the assignment is not valid. Okay, so therefore the assignment is not valid. So assignment E is not also valid. So we have seen here assignment A, assignment B are valid. Assignment C, assignment D, and assignment E are not valid. Okay, so two assignment are valid, and three assignment. Okay, last three assignment are not valid. Okay, students, clear? So this is very simple. Okay, and basic concepts. So I hope it is clear to all of you. Now we will discuss probability of an event. Okay. So first we let here is be a sample space associated with the experiment. Okay. Examining three consecutive paints produced by a machine and classified as good and bad. Okay. Good means non-defective and bad means defective. Okay. And we may get 0, 1, 2, or 3 defective pens. Okay, as a result of this examination. So we have taken here this random experiment. Okay, uh, ta- uh, uh, getting 0, 1, or 3, 0, 1, 2, or 3 defective pens. Okay, so basically 3 consecutive pens produced by a machine here. Okay, and classified into two types: good and bad. Clear? So a sample space associated with this experiment is, so what is the sample space associated with this experiment? So student, you can easily write sample space associated with this experiment. Clear? So sample space S is nothing is sample space containing the sample point. BBB, what does mean? So BB means three consecutive pens, okay, produced by a machine, okay, and classified as bad. Okay, three pens may be bad. Okay. And second sample point we have PVG, means two pens. Okay. First two pens bad and last pen is good. Okay. Or it may be first pen is bad, second pen is good, and third pen is bad. Okay. Or it may be first pen is good, second and third pen may be bad. Okay, defective pen. Okay, like this. So here the sample space is containing BBB, BBG, BGB, GBB, BGG, GBG, GGB, and GGG. Okay, so this sample point containing the sample space is here. B stands for a defective or bad pen. Okay, and G stands for non-defective or good pen. Clear, students? So note this point. B stands for defective or bad pen, or G stands for non-defective or good pen. Okay. Now let the probabilities assigned to the outcomes. Okay. So the probabilities assigned to the outcomes be as follows here. So here you can see sample point. Okay. Uh, for sample point BBB, what is the probability? So probability of BBB is basically 1 by 8. Okay, how we get here? So you can easily find. Okay, so here you can see P of B equal to 1 by 2. Okay, and P P of B equal to 1 by 2, and P of BBB is, this is nothing but 1 by 8. Okay, so probability of all the sample point will be 1 by 8. And since we know that probability of B is 1 by 2 and probability of P of G, okay, P of B is equal to 1 by 2 and P of G equal to 1 by 2 also. Okay, so a pen may be bad pen or maybe good pen. Okay, so there basically we have 50-50 chance. That is why we assign here P of B equal to 1 by 2 and P of G equal to 1 by 2 also. Okay, so P of BBB, this is equal to 1 by 2 multiplied with 1 by 2 multiplied with 1 by 2. Okay, and this is equal to 1 by 8. Okay, and similarly you can find probability of BBG, probability of BGB, probability of GBB, probability of BGG. Okay, and probability of GBG, probability of GGB, and probability of GGG. Okay, so probability of all the sample points are 1 by 8. Clear? So note this point. Probability of all the sample points are 1 by 8. So now we let here event A. So what is event A here? So event A describes there is exactly one defective pen. Okay. And what is event B here? Event B describes, denote the event where there are at least two defective pens. Okay, so we first let here event A and event B. So hence here A is nothing but set B, GG, GBG, and GGB. Okay, so there is exactly one defective pen. So the event A containing all the sample point. Okay, where the sample point are BGG, GBG, and GGB. Okay, and similarly the event B containing BBG, BGB, GBB, and BBB. Clear? And now P of A. Okay, P of we have studied in axiomatic approach of probability. Okay, so there we have seen P of A is equal to basically summation of P of omega I, where omega I, for all omega I belongs in say event A. Okay, so this is equal to P of BGG plus P of GBG plus P of GGB. Okay, and as we have seen, the probabilities probability of all the sample points are equal to 1 by 8. So this is equal to 1 by 8 plus 1 by 8 plus 1 by 8 3 times, and this is equal to 3 by 8. Okay, so P of A equal to 3 by 8. So probability of event A is equal to 3 by 8. Also P of B, this is equal to summation P of omega I, for while omega I belongs in event B. Okay, and this is equal to P of BBG plus P of BGB plus P of GBB plus P of BBB. Okay, so probability of all these sample points are 1 by 8. So this is equal to 1 by 8 plus 1 by 8 plus 1 by 8 4 times. Okay, and this is equal to 4 by 8. Okay, and this is equal to 1 by 2. Okay, so probability of event B is equal to 1 by 2. So now let us consider another experiment. Okay, so now we are considering an experiment where are tossing a coin twice. Okay, so now we are tossing the coin twice. Then what is the sample space? So the sample space of this experiment is equal to uh, HH, HT, TH, and TT. Okay, so if we toss a coin twice, then we will obtain the sample space is equal to set HH, HT, TH, TT. Clear? And let the following probabilities be assigned to the outcome. So P of HH, this is equal to 1 by 4. How we get? Since P of H equal to 1 by 2 and P of T equal to 1 by 2. Okay, so